3, so that's a deep network, right? So it's got an input layer, an output layer, and then hidden 1, hidden 2, hidden 3. And I said this can be, in most respects, equivalent to one that is like this, but where these 3 become 1. So let's say this is A, B, C. So then A, B, C, and the output. Do you see that? So then you might ask yourself, well, if there are theorems that say that this is possible, then why do we need deep learning? Because we could just do everything with a network such as this, which only has one hidden layer. Do you guys get the idea? And although the theorems say that this is possible, there's a problem. If this is a CNN that has 50 layers and the layers have tons of neurons, then this one layer would end up having possibly 1 million neurons. Imagine, as a big thing. And also what does that do? Just in terms of computing power, well, you're going to have to do a matrix multiplication between this and that. That's a lot of resources. Do you guys see that? So that's one issue. The other issue is that actually the relationship, although this is possible, there's a growth, an exponential growth also. That is to say, you can't just take these neurons of size n, right? Now you would have to take these neurons but of size m, where m is much bigger than n. Does that make sense? So it's not just even copying these 3, but it's copying these 3 with more neurons. So you can make it, so this is depth and this is width. You can increase the width, but it's possible to have one layer, but the move of the neurons is not linear, let's say, more exponential. So that means that whereas these are size n, these are size m, the number of neurons, and this just implies they are much bigger. Not just bigger, much bigger. Does that make sense? All right, so I wanted to kind of clarify that one. And in general, you can read through the 3 papers. I just trust them, so we're not going to have to prove that any of that is true. But basically, it does kind of imply that, one neural network can do it, but it doesn't make sense. So this is better for constraints and also in terms of the amount of neurons, basically. So depth is a good thing. Okay. All right. So that's kind of one of the things I wanted to say. This is the preferred way. But you can read through those papers historically, and this just goes back to this idea of the universal function approximator, which basically means, any function can be approximated by a neural network, right? So, what that kind of implies also, let's say that you want to build a quadratic function, or you could just build a a function that is made by a neural network, because you remember a neural network takes inputs and outputs, right? It'll figure out some structure. It can approximate that one. It can approximate a polynomial function. It can approximate, and in fact, the theorem says it can approximate any function you can think of. So in theory, do you have a theory about giving it stock prices now and telling you what you should buy or sell? That's a function. Do you see that? So the implication of that is not just, geometric functions like these. Remember that a function is literally any input that's processed, transformed, and gives you an output. So it's got very big implications as to what that actually means. However, they do constrain it in saying, okay, within this scope, but there is a higher implication there, that it can approximate a lot of behavior, because at the end of the day, machine learning is just inputs that go into a network, and then you get outputs, right? And you have to train them. Does that make sense, guys? Any questions?